Well. Okay, hello everyone. Thanks for having me here and thanks for your interest in this presentation. Today we are going to talk about modularity for decidability. We want to use decidable logics in deductive verification. We also will talk a little bit about applications of this methodology in distributed systems. Of course, everyone can read the paper to learn more how we use that in distributed systems. I am Marcelo Taube at the top left. My mentors, Muli and Sharon, are there. We have a very nice team from UCLA, Microsoft Research, Washington University, and Tel Aviv University. Among them, Ken Macmillan, who is leading this practical research on decidability, and he writes the tool we use to implement our ideas, Ivy, Microsoft Ivy, worth checking it up. Now, in our research, we are concerned about effort, we are concerned about productivity of the verification. So in our world of deductive verification, there are, let's say, two main branches we consider. One is the proof of system methodology, which has been really successful in the latest years. And the other one is the using automatic solvers like Z3. Both of them require quite an effort to get things done. The proof of system, of course, requires to write a full proof manually. Each reviewer would also need to see it to understand it. And the automatic solver tries to offload work to algorithms that try to solve problems in the SMT language. But the problem with this is that even if the proof is done by a machine, still the problems are undecidable, and there is no guarantee the solver will terminate. And in particular, it's not only a problem of whatever it terminates or not, because it can be tuned, it can be the solver can be helped to terminate, but it's also important the stability. If you change a little detail in a formula, will it still terminate? Will it take 100 times more? So you need to do lots of work to make this continuously verify each iteration you do in your proof. So unpredictable verification hurts productivity too, even if it's automatic. Now, as we said, productivity is really important. Our proposal is to use decidable logics to improve this thing. We have an hypothesis that if we use decidable logics, the solving time will be much more stable, and the process of verifying will be much more effective. It's an hypothesis we like to check. And I think this work is a good start to check the hypothesis. Now, I want to give you some intuition of why automatic solvers can fail. Let's take, for instance, Z3 and other SMT solvers, which can solve first-order logic and also can add arithmetic and array theory. So if you use the full power, all of these features together, you will be in undecidable ground. You have good chances that Z3 will not be a decision procedure for your formula. Now, suppose you do want to be in a decidable fragments. Will you able to do it? So namely the answer is no. Why is that? Because as we said, if you use the full power, you are outside of a decidable fragment. Now, what we are proposing as a solution in this paper is that undecidability happens when you use all the features together. It's like a mix and match of features. Now, if we can split them back to separate verification conditions, will we be able to be in a decidable fragment? We think in many cases we can do that. So in this work, we will leverage standard modularity techniques, and we decompose system to components to be able to prove the behavior of the system. Now, for this presentation, we are proving simple procedures which have preconditions and postconditions. The preconditions and postconditions have to be expressed in an SMT formula. The code is automatically translated to a transition relation tau in this case, and then the solver gets to check if this formula is valid or not. So now, how can we make these things decidable? So again, if we just take a random program and take it and generate the verification condition, not sure we will be decidable. But then what we want to do is split the verification condition into parts, check them separately, and do this, of course, in a sound way, and check each one in a maybe different decidable fragment. So now we will go over a micro example which shows how this technique works, so we can get the point across. It's not in a distributed protocols, but later we will talk about how we use this in distributed protocols. So first of all, in our example, it's about elections. So like in each election, we have citizens. The elements we talk about in the program will be citizens. We also have set of citizens. We use those to represent the set of voters for a certain candidate. And finally, we have integers. Integers represent the cardinality of those sets of voters. In our state, we will have voters, the voters function, which maps for each candidate, which is the set of voters which vote for him. We have also a leader relation, which says for a candidate wherever it has been elected as leader already or not. And this is our very simple procedure, which was engineering to have all these features we talk about, which make undecidability. So what does this procedure do? It checks for a given citizen whether the citizen can become a leader or not. If it can become a leader, it will be the relation is leader will be automatically updated to true. And this procedure can be called for each one of the citizens to check whether the is leader relation should be updated for him. We have a post condition we want to prove for this procedure. We would never have to like to have two leaders at the same time. That would hurt the purpose of holding elections at all. And before this function runs, the previous procedures, which we don't show here, which fill the voters relation, need to guarantee that each one of the voters voted only for one of the candidates. So this is a precondition we need for the proof of the single leader property. And another condition we need is that if by chance, before this function ran, a leader was already elected, it was elected because it has enough voters. Given these properties, even if we check again for the same leader, for someone, if it has been elected or not, we cannot choose two leaders. So there is an implicit proof here that the automatic prover can fill for us, but unfortunately, it's not decidable. So the first thing, so what we want to do is split this procedure into separate modules. We will use some interprocedural modularity at this presentation, And our goal is to be decidable. So the first thing we want to do in this example is to split away the use of arithmetic. The way we will do that, we will have two modules, one in first order logic, still undecidable at this time, and the second one, which we will call the sets module. This module will be proven in the finite, almost uninterpreted fragment. It's a decidable fragment already published by another team, and this fragment allows arithmetic, allows some limited use of uninterpreted symbols. And in this fragment, we can prove the sets module. Now, this is our original procedure. As we said, we will split in two modules. The sets module would have to export some new symbols. The is-quorum relation would tell us for each set if it's big enough. The property we are just checking right now within the main module. Another thing we will need is to have a function we give if there is a citizen available in the intersection of the two sets, it will provide it for us. The reason we need this function is to state this property, which will be needed in the proof. If we have two sets which are quorums, they need to intersect in a valid member which belongs to both of them. This parity will be public and will be seen in the main module for the global proof. And privately within this module, we will know that this quorum is defined as having a set big enough, bigger than including more than half of the nodes of the system, of the voters of the system. Now, the last remaining thing to become modularity is to replace the original code by accessing the is-quorum property instead of using the set cardinality and doing arithmetic. So we replace that in the main module. And now, in this talk, we will focus mainly on the main module, and we will not prove the sets module, but if you are interested, you can read the paper, of course, or talk to me offline. Now, in the main module, we are in first order logic. That means we have no interpreted theories, but we can still be undecidable, of course, for first order. And we want to understand a little bit why first order logic can be undecidable. So one of the reasons is this. Suppose you have a big formula you want to verify. You have two types of elements in this formula. One is type T, one is type S. Now, in the formula, you have one constant mention T. This is one of the ground terms of the formula. Now, of course, what the solver tries to do all the time is to derive new knowledge, to derive new information, to reach conclusions. So we have a quantified formula for all elements of type T, and we have an element of type T. We can, of course, apply quantified instantiation and derive new knowledge. What else do we have in this formula? We have a function from type T to type S. We have we can apply this formula, this function, and we get a new ground term of type S. We have another function from type S to type T. Again, we can apply this function again, and we have a second ground term for type T. So what happens when we have a second term of T? We can derive even more new knowledge. We can apply the quantified instantiation also for this ground term. This is exactly how the solver derives information. Now, what's the problem? What's the problem with these two functions, f and g? They generate a loop from type T. So each time you apply f and g, you can generate a new term, a new term, a new term, and you are searching. You can derive infinite number of new information, and the solver is searching within an infinite search space. So the bad news is that if you have a formula like this, it can be not decidable, but if we somehow can limit this, we can be within a decidable fragment. This decidable fragment is called effectively propositional logic. It's a subfragment of first-order logic. It doesn't allow us to have functions loops like I showed. And if we are in this fragment, the problem becomes decidable, of course. Now, we want to look at our relation program and ask ourselves, is our program EPR? No, not initially at least. So we have two functions, the common member function, which intersects two sets. This function is used in the proof. The voters function is used in the code itself. And we have this loop, so verifying the correctness of this module right now is not in the EPR fragment. Now, our solution at this step is to split the main module to two modules, which we will call main module and votes module. Each one of those will be verifying the EPR fragment. And the interesting thing is that we need one of the functions to prove part of the proof, and another function to prove the rest of the proof. So let's try to make this in EPR. First of all, the condition in the if loop will be moved to another module. We generate a new procedure, enough votes. We split the two modules. We will replace checking this condition directly by calling the enough votes. Of course, this can be inline, so it's not affects performance. Then, at this stage, to verify the main module, we can still see the voters. So we are not really in EPR yet. But what we want to do is to hide the implementation of this procedure and specify it using a specification, a post condition for the procedure. When we do this, we change the shared vocabulary to have a relation instead of a function. And at this stage, each one of the modules can be checked in EPR. So this final solution has three modules: main module, votes module, and sets module. Checked in EPR. The first two are checked in EPR. The sets module is infinite and uninterpreted, and in this way we can use decidability. Now, we use this decidability to check distributed protocols implementations. We implemented Raft and Multipaxos, two consensus protocols in Ivy. We verified them also using three modules. We can compile them to C++. And we did some sanity checks on the performance to make sure our methodology is not constraining the skills of the programmer. And we get good performance results. Our proofs are only to state the invariant, so of course they have a very small ratio of lines of code to lines of proof. We show here two projects, Verdi, that implemented and verified the Raft protocol with Coq, and Ironfleet that implemented with Daphne. It's not apple to apples because Ironfleet has a little more features, but you can see that this methodology is pretty effective, much smaller ratio of code to proof. And something else we did is to evaluate how well we do with human effort. So we were able to prove the two protocols in just a few months. The interesting thing is that we really wanted to make the verifier efficient. We were able to verify our implementation of Raft and our implementation of Multipaxos in a few minutes on a laptop, while other projects have to have half an hour to verify them, or have to distribute it in a cloud for 6 hours to do the full verification. So these results are better. And finally, I want to state what were your the contributions of our paper. We created this methodology, modularity for decidability. Modularity is standard, but now we are using it to achieve decidability, and we see that at least in these examples, it was really helpful to achieve decidability. We incorporated 2 new features in Microsoft Ivy to test this methodology, modularity itself and the compilation feature, so we can check the implementations. So we applied those to verify distributed consensus implementations. And we're happy to see that decidability was possible, it paid off, and we were able to verify in less time. And that's all. Thank you.
Hi, great talk. So I have kind of 2 questions. First is just clarification. When you say manual proofs in your evaluation, do you mean those sort of abstractions, more abstract specifications that you have to put on the modules?
When I say manual proof, I am talking about proofs which use proof assistance and
no, because you had lines of code of proofs for your method as well.
So
right?
when I say manual line proof, I'm saying any line I'm adding which is not the code itself, which is not the
right, so
executable
specifications
code.
basically.
Yeah, so it's everything I've shown here in comparison to other methodologies.
Mm-hmm. And the second question was, so do I understand correctly that this is just a methodology that basically informally prescribes, for a programmer, this is how you write those specifications to make the model, or is it the language limitation that actually tells you, okay, now it's decidable? And
so the verification tool itself checks that the way you split the modules is in one of the decidable fragments the tool knows. Of course, the methodology it's much more flexible and can be used in a different scenario with different tools, but that's the idea.
So it would tell you if you got it right, but it doesn't help you design those.
No, you need some creative work, some creative. It's not fully automatic.
Right.
It's like a middle ground between automatic and completely manual work.
Sure. Thank you.
Thank you.
Thanks for the great talk. Maybe there's a follow-up question. So you also mentioned about the human effort for the verification. It is surprising that if you just use some modularity and some decidable logic, I can understand that reduces the verification time. But do you also want to claim that reduces the human effort because of that modularity and decidability?
So first of all, the numbers we report here, if they are not from our project, are from the numbers themselves that the authors reported. But mainly, I think the reason, even if I don't have much personal experience using Daphne, so I think the reason it takes less time, as much as I heard, is that the verification with Daphne, you need to help Z3 to reach the conclusion, because it can diverge, it cannot stop. So you need to do some work of tuning of the verifier to make it achieve. Our way of dealing with the diverging is to, in advance, write the verification conditions in such a way that are decidable. Another methodology, which I think is that they do, is fine-tune, do some pattern matching, help Z3 to solve an undecidable problem. So it takes a lot of time. When you are verifying, you do lots of iterations. You start, you write something, it's wrong, you get a no response from so you need to do lots of iterations. Each one of these iterations takes time or does not finish, it hurts your productivity. So I think that's the reason.
Okay, thanks.
Thanks for the great talk. So could you tell me what kind of safety property did you prove for multiplexers and the rest?
So the property we proved
Yes.
is I think it's called consensus. Or,
yes.
So basically what they do is that if one of the nodes reaches a conclusion for one of the log indexes, and another one of the nodes also reaches a conclusion for that index, they agree. They have no disagreement at no point in time. That's the safety.
Yeah. And the another question is, I've heard that you restrict the number in the round. You restrict number in between the two modules in the communications.
Sorry.
You restrict the number of the communications in between two modules in the slide.
You mean there's a bounded buffer size?
Yeah, bounded buffer size. So
The bounded
buffer size for messages. I think we'll do that. I don't remember seeing that in the paper.
bounded buffer size in messages. It's something we mentioned in the paper.
Network modeling.
yeah,
I think I remember hearing you say that, so I don't know. I don't quite
Yeah.
understand the
So
question.
okay.
yeah.
Okay, I understand your question. It's not something I talk about, but okay. So when you are proving safety, you are talking and reasoning about things that won't happen. You want to prove that no bad things happen. So if messages get dropped and you cannot communicate with the other side, you will still be able to prove safety of the implementation. The problem is when you go to prove liveness, you will need to prove that the messages will arrive. We didn't prove liveness in this work. We are planning on working with that. It's not the limit on the buffer size is not a main part of the methodology. It's just a low-level detail that was not important for this work. So,
Thank you.
I think we've run out of time in this session, so we can take this question to the break afterward.
Sure thing.
Let's thank the speaker again.
thank you.